Hello, class. This will be the recorded lectures for section 5.2, which talks about rational functions. They're complicated. Just to start off with, rational functions are functions where there are fractions. And basically, our definition will be there'll be a polynomial on the numerator and a polynomial on the denominator of these rational fractions. So our ideas and analysis are split up into two sections. The first section is to talk about the key attributes of the rational function, which will include the intercepts, which we've talked about already. Plus, we'll talk about this idea of domain and these ideas of asymptotes, and they'll all be kind of tied into this. What I'd like to do before we get started is to show you the simplest rational function there could be and show you kind of how complicated it is. So the simplest rational function would be f of x equals 1 over x. Can't get any simpler than that, right? Well, we've talked about this idea before. The domain, we can't divide by 0, right? So the domain of this function is all values of x such that x does not equal 0. I personally don't like this notation, but unfortunately, I can't change my math lab, and they use this notation in the homework. So I want you to be familiar with that. And so x can't equal 0 is basically the bottom line, because if we divide by 0, we don't have a real number. So how would we graph this? Well, say like we wanted to graph this thing, and you would just start plugging some numbers in. So what the heck? Let's just start plugging numbers in and see what we get. So we can't plug in 0, so the best number to plug in is 1, and 1 divided by 1 is 1. If you plug in 2, that would be 1 over 2. If you plug in 3, that would be 1 over 3, and so on and so forth. So if we put and say this is the number 1 and that's the number -1 to give us some space there, right? What ends up happening would be 1. Let me do this in a different color here. So blue would be, so it'd be 1, say that would be a half. That would be a third, that would be a fourth. And so you could see that the graph would end up going this way. It is never going to touch the x equals 0. And this is actually called a horizontal asymptote, and we'll teach you how to calculate that. I'm sorry, y equals 0, right? The x-axis is y equals 0. And during this, we'll show you how to calculate that. So you can see that we have a few points here. Well, what happens on the other side? Well, this would be, say, between x equals 1, and remember, we can't plug in 0, x equals 0. So say like we went in the other direction. Say like I plug in x equals 1/2. Go back to red. And so it'd be 1 over 1/2, and that would be the number 2. If you plug in 1 over 3, it'd be 1 over 1/3, and that would be the number 3, and so on and so forth. 1 over 10 would be the number 10. And so you would see that this graph would shoot all the way up that way. It's never going to touch the y-axis as well, and that's when x equals 0, right? And that's actually called the vertical asymptote. Again, we'll show you how to calculate that a little bit later on in this section. So what happens on the negative side? Well, let's take a look at that, see what happens. So again, the same idea. Let's say -1 would be -1, right? -2 would be -1/2. -3 would be -1/4, and so on and so forth. -10 would be -1 over 10. So again, if we did this calculation on this side, this would be -1, right? This is +1. This is -1 over here, so I'll put it in blue. it would look something like this. And as you keep going, again, it'll never hit the, that's not a very good drawing. Try again. Because it's never going to hit the x-axis as well. And the x-axis, again, is y equals 0. And that's going to be called our horizontal asymptote. So the last thing is what happens between x equals -1 and x equals 0. So if we take a look at our little table here again, and we start plugging in numbers, -1 again is -1. -1/2 would be 1 divided by -1/2, and that would be -2. And I think you see the pattern. This would be -3, ... And if you go all the way down to say -1/10, that would be -10. So if you plotted that, you would see that you would get continuing, and it would go that way. So if you see what I mean, the simplest of the rational functions has a quite complicated graph. And so as you can see, I think this section is going to be a little bit challenging. So what I'm doing here is pulling up Desmos. And if I share my screen here, oops, wrong share. Try again. There we go. If I share my screen, you can see that I typed in y equals 1/x, and you can see what a crazy graph that looks like. But you can see it never touches the x-axis. And so this is y equals 0. That's the horizontal asymptote. And it never touches the y-axis, and that's going to be our vertical asymptote. So moving on, let's talk about, first of all, how to calculate domain. And so the domain of the function is going to be calculated using the original equation. So there's going to be two versions of the equation. One is the original, and then you're going to ask yourself, can I simplify that equation by canceling like factors in the numerator and in the denominator? But when you do domain, it's always with the original function. And so let's go through a couple examples, and I will do these on the whiteboard here. I keep clicking the wrong thing, sorry. Whiteboard. So when we get to the whiteboard, let's take a look at a function that looks like this. F of x equals x minus 2, x plus 3. So original equation, what you want to do is you want to make sure that the denominator does not equal 0. So x plus 3 cannot equal 0. We've done this before, right? X cannot equal 3. And interval notation, it would be -infinity to 3, union 3 to infinity. And in our set notation, and this is what my math lab is asking for, all values of x such that x does not equal 3. Okay, so far so good, hopefully. And let's do another one. So say like we take this one. F of x is x minus 2 over x squared minus 4. So when you do this, sometimes it's nice to do a little bit of factoring. And you can see that we could factor the denominator, and it would be x minus 2. And it would be x minus 2, x plus 2. But when you do the domain calculation, do not cancel these two out first. So you have x minus 2 does not equal 0. And so that implies x does not equal 2. And then you have x plus 2 does not equal 0. And that implies x does not equal minus 2. So when you take a look at this, you have 2 points that are not in the domain. And again, I'm going to do the set notation because this is what you need to do in your My Math Lab homework. All values of x, this vertical line means such that x does not equal minus 2 or 2. The interval notation would look like this. I find this to be a better description personally, because this looks like what the number line would look like with regards to that. Hopefully so far so good. Let's do a couple more. So say like we had this one, f of x equals x cubed over x squared plus 1. So then you say, okay, you want x squared plus 1 cannot equal 0. So you would have x squared equals minus 1. And then you say to yourself, can I do this? Take the square root of both sides. What does that equal? That equals plus or minus I. Remember, did the complex number, so this is not a real number. No real numbers. So there's no real number that will cause this equation to be 0. So in this case, this would be, domain would be all real numbers. On the other hand, if we took this and I changed this to a minus, and then you could see this is factorable, but if we do it this way, x squared minus 1 does not equal 0. So then x squared equals 1. Then if you took the square root of both sides, you would see x, whoops, not equal there, does not equal plus or minus 1. And so that would be, again, x, all real numbers, x, such that x does not equal minus 1 and plus 1. Cool. So I think that's a good start with the domains. And the next recorded lecture, we'll talk about the asymptotes.